So we conclude today's second part of the lecture by looking at label shift. And part of the reason why we had to go through all this lead up in terms of two sample tests is because for label shift, the situation is a little bit more subtle. And so we need slightly fancier statistical testing procedures than what we needed for covariate shift. So suppose I have, again, my training and test set, and I want to classify cats and dogs, right? As I would, right? And of course, again, I build my classifier and it does a good job distinguishing cats and dogs. But then at test time, well, we get this. So we get lots more cats. And the problem is, as we get lots more cats, well, the system may not actually then work so well. And we should probably be adjusting our estimates a little bit. And that sounds, a patently silly example. Why would anybody be so stupid to actually design something like this? Well, there are plenty of cases when this happens. So for instance, you might try to build, a test for, diagnostics for COVID-19. And so, you train this on data with, relatively few sick patients. Let's say, for instance, what we have in California right now. But then you actually go and, test this in South Dakota after the Sturgis biker rally. And, this caused a massive spike of COVID-19 last year. So it was such a great success that they decided to repeat it this year, right? With, very predictable results, maybe a little bit better because more vaccinations. But in any case, what happens is now suddenly there are a lot more sick patients again with COVID-19. So what that means is, Q of COVID-19 is much larger than P of COVID-19. But, you would hope that even Sturgis and all of that at least the virus itself didn't mutate, it just reproduced. And so therefore, the distribution of symptoms is still the same as what it was before. And let's assume that bikers don't have vastly different COVID-19 symptoms from other people. Okay. And after all, they make their families sick and everybody. So long story short, symptoms are the same because we can pretty much assume similar strains, but a lot higher prevalence. And so you want to adjust your classifier for that. Likewise, you could think about, speech recognition system, and maybe it's trained on data, newscast data before an election, and then you have an election, and suddenly different people get voted into office. And so you want to, test on the newscast after the election. And so there are new names and all of that. They still speak English, presumably, or whatever other language there is, but, it's new people, new topics. And sometimes elections happen because people want to hear new topics. So what happens thus is we need to correct for the different prevalence in the outcomes. And this can actually be done quite straightforwardly. So let's assume that we actually know P of y and Q of y, and let's assume that we have a trained model with P of y given x. Actually, if I had to be really pedantic, I would put a hat on P because, well, obviously this is an estimate, it's not the truth. So, but what we want to do is we want to get an estimate of, Q of y given x. And remember, we know that Q of x and y is Q of y times P of x given y. So what can we do therefore is we can, use Bayes' rule, right? So we want Q of y given x, and Q of y given x is just, Q of x given y. This is just Bayes' rule times Q of y divided by Q of x. Okay. However, we know that Q of x given y is the same thing as P of x given y. Okay, so this is fine. It's the same term here as what we have there. And then what I'm doing is I'm just multiplying and dividing by p of x, right? And I'm multiplying and dividing by p of y. Okay. So if you recall the remaining terms, so q of y and q of x, they persisted from before, but now we have, those three fractions. The first thing we can do is we can realize that this block here is just constant, and therefore we can make it go away. Secondly, we can also realize by Bayes' rule that the first term here is just nothing else than p of y given x. Right? Because in the numerator we get p of x and y, in the denominator we get p of x. So that's just p of y given x. And that leaves us with the all-important correction term, namely this one here, which persists. So in short, what I get is that q of y given x is nothing else than p of y given x times the ratio between q and p of y's. And that's actually a super intuitive model. All it means, for instance, in the case of the Sturgis-Spiker rally, is that afterwards you take, the posterior probability for COVID as you would have, but you now bump it up a little bit by the ratio between, in this case, the infected and correspondingly the healthy patients. Now, besides, COVID-19, this is, for instance, a real thing that you would need to do for an AIDS test. Let's say you want to deploy an AIDS, you want to test whether they're HIV positive, right? AIDS is just a set of symptoms, but basically if you want to deploy that test in, somewhere, sub-Saharan Africa where, the infection rate is quite high, you would thus take your test that you may have calibrated for, again, California, and you then upweight your corresponding probability estimates because the prevalence of HIV positive people in sub-Saharan Africa is just so much higher. This is something that we would intuitively do anyway, but now here we have an explicit formulation. Mind you, the last term is just, it's still unnormalized. So what you still need to do is you would still need to sum over p of y given x. So basically this term plugged in for y equals 1 and y equals minus 1, for instance, and normalize it to 1, right? So that's a really important detail, that this is just proportional. Okay. So to make a long story short, if we, have p of y given x and q of y, we don't actually even need that, training set up, but if we just have those things, then we can, at test time, adapt our estimates simply by, running the original model and then reweighting the estimates. And then you renormalize. Okay. And in many cases, you'll be lucky enough that this is the case, and you should take full advantage of the data when the data is nice to you. So a good engineer always takes advantage of any data that you have available, so don't try to estimate the more complicated thing if we can get away easily. Even if the algebra then turns out to be less intimidating, it's actually a sign of being, a good statistician that you find a simple solution. Now, the problem is, in general though, that, if we don't actually have, q of y, then, and on top of that, if we want to, get, the proper risk minimizer, then we need to become a little bit more creative on how we can go and estimate things. So the first thing that I want to cover is how you would actually have to reweight your data. And what you can see is that if I have an integral, dq of x and y of L of f and x and y, so that's my risk. So that's basically, so to say, the risk of f and q, and of course also the loss function, that this risk can now be written as a q of y integral times dp of x given y times L of x and y. Okay, so this is again just, using conditional probabilities, carving out the first term. And so now what I can do is I can, of course, replace the q integral by a p integral, and then just the ratio here. And furthermore, what I already did here is I used the fact that p of x given y equals q of x given y. After all, that's the assumption, right? And so now I can, pull this back out, and so I get, p of dp of y, dp of x given y. So that's again dp of x and y. So that's, the integral over the training set. But what I do here now is I end up reweighting the y's according to that ratio. So that's important. So if you're able to get the appropriate importance weights for the y's, and so they depend on the y's only, then you can train the effectively reweighted data. Right. But as said, the big problem is that, we don't really have the samples from Q of Y, so we need to figure out on how we get them in the first place. And this feels a little bit like a chicken and egg problem because, hey, if we had it, we could train nicely, but since we don't have them, then we cannot train the correct thing. And again, we are going to go through a number of strategies on how to do this. And actually, the spectral algorithm is one that you will be expected to do in the homework. Namely, the key idea is you want to measure some statistics in the test set. And so let's assume we had some, maybe not so great classifier which estimates, some, p hat of, y given x. So this is not, the true estimator, but that's just, whatever, our system does. So what I can do is I can therefore then look at the confusion matrix. So this is our error confusion matrix. And you'll get to compute that in the homework. And that's nothing else than the integral over, my predictions, right? Given x, okay, as you would. And now I need to integrate over x, right? Over x given y. So p of x given y, I have that, times p of y. So in other words, I could write it out as p of x and y. Now the good thing is I actually have access to this, right? Because this is exactly what I draw my training data from. So I draw my xi's and yi's are drawn from p of x and y. So with that, and without much further ado, I can actually work out exactly how to get p of y hat and y. Namely, just for every value of, y, look at the probability vector p hat of y hat given whatever, we get there, and just aggregate. And I'll show you the pseudocode on the next slide. And on the test set though, I obviously don't have, the true labels. So on the test set, I can only get the distribution of, p of y hat, of q of y hat. And q of y hat is given by p hat, right, of y hat and x, given q of x, given x times q of x. And so now this is just, the integral over that, test distribution. So remember, on the training set, we have the y's, so we can actually get p of y hat and y. On the test set, we don't have the y's, so we can only get this. And so we get thus in the end, q of y hat. But we also know that q of x, that q of y can also be written as, let me write it out. This is nothing else than, p of y hat and, given y times, p of y. Okay, so now we want to replace this with the weights times q of y. Let me just quickly make a bit more space. Times, q of y. But obviously we don't have that, so what we need to do is we need to multiply by p of y divided by p of y. And this is exactly beta. That's beta. And so the original term is exactly this one here, right? So the combination of these two terms is exactly that one. So that's how this equation comes about. So q of y hat is, p of y hat and y times beta y. And the good thing is this has to hold even if, my p of y hat given x, and also the estimate p hat of that, if that's, not very reliable. That doesn't matter. Now, let's, work out the simple algorithm. So I go and initialize the matrix and the vector here. So this is a matrix, this is a vector. I initialize them to 0. And then I first go over the training set. And whenever I encounter a specific yi, then I go and, increment the corresponding conditional probabilities, right? This is literally how you would implement it. And then on the test set for I equals 1 to m prime, you basically increment p of, actually this really should be p of, y hat, yeah, it's the same thing here, given xi and x prime I, right? So I get the matrix and the vector. I do need to normalize suitably. So what I forgot here in the pseudocode is, q goes into 1 over m prime q, and furthermore c goes into 1 over m c. And if m and m prime are the same thing, then I can leave them out. So this is why I was too sloppy here. And then I get those weights, beta, as just c inverse q. Why is that? Because on the previous slide, we had exactly written that q is c times b. And then I can solve the system of equations by just working out b equals c inverse q. Now that's great. There are a couple of safeguards that they may want to employ. One of the safeguards is that all the betas be non-negative. And I also want to make sure that the betas are suitably normalized. So in other words, that the sum over y, q of y, equals 1. But since I know that this is nothing else than b of y, right, times p of y, I can therefore directly enforce that this also holds. Now, for your homework, you'll only have to solve this expression here, because I didn't want you to have to learn how to use a quadratic solver. Also because there are a couple of alternatives that you can use, namely where you minimize a negative log likelihood that works at least as well as this. But this is just, a useful baseline, and you'll see that it's actually fairly accurate. Now, one of the nice things is, and this is a fair amount of detail that I've hinted at but didn't really prove, is that even if the estimates of y hat of x are wrong, the calibration is still okay, right? Because we are still assuming that we make the same errors on the holdout and test set. The other thing is we one of the ways how you prove this is, for instance, that, the matrix C and, the vector Q have, that they are concentrated, so we can use a matrix Bernstein inequality, or, just otherwise just standard concentration inequalities for the vector. Furthermore, the other thing that I skipped a little bit is that what you really want to do is you want to train your classifier on some data set, and you want to have a small holdout data set for calibration. So this is drawn from P, this is drawn from P, and this is maybe the entire, test set drawn from Q. And you basically want to hold out a small amount of data for, calibrating your estimates of C, because otherwise you will get somewhat biased estimates and the algebra doesn't quite work out. So in many cases you can get away with being sloppy. In the homework, you're actually allowed to be sloppy rather than having to set aside yet another separate data set. But that's a minor detail that you need to be aware of if you want to do this for real. So does it work? Yes, it does. And so if you basically go and just, use the unweighted tricks, then you get not as good accuracy. And if you use, the black box label shift estimator, that's what it's called, BBSE, then it works quite well, but that's just a minor detail. Now, there are a lot of extensions that we did not cover. For instance, in some cases you have streaming data, so where the weights change while observing the data, and then you can maybe run SGD through moment matching. We didn't look at really large feature sets. We didn't look at GANs, so there are lots of other tricks that you can use there. And then the last thing that we didn't cover is how to use the Kullback-Leibler divergence to calibrate Q of y against beta of y and P of y more accurately. So if you think about it, what you basically end up doing is you would want to, for instance, in a maximum likelihood sense, you would want to optimize the log over basically, P of y times, beta of y sum over the y's, and you would want to optimize that quantity on the test set, right? And that, of course, will give you nice maximum likelihood setting. So there's a fair amount of interesting detail there that we didn't get to cover because this is a practical machine learning class, but I hope you at least have some basic tools to know what to look at and what to go further. So this sums up the second half of lecture 7. There's a large number of things that we didn't cover at all. One of them, for instance, being covariate drift. You may have, geographic preferences that change slowly. Things may change slowly over time. And in that case, you can then essentially adorn your, covariate drift estimate here by something like, for instance, time. Or we could have space, right? And if you do that, you get a very convenient function that now will allow you to, compare, let's say, how the distributions, changed between time point 1 and time point 2. So you could, for instance, ask questions like, how much differently are people behaving now as opposed to 2 years ago versus now as opposed to 20 years ago? The reason why this is difficult in general is that basically if you, assume that you get only one observation at a time, you have this changing distribution, right? So this is, P of x and t, actually given t, right? And yeah, these needs to be really conditions. And then what you do is you get only really one observation at any time. And so you essentially need to perform covariate shift correction where you only have a single sample at any point in time or at any point in space. Let's say you want to find out, how trees differ as you look at trees that are further north, and maybe there's also an east-west dependency. And so therefore you then really need that ratio function, right? And ratios are easily modeled by e to the difference between things. And you can train that directly. So this is still interesting new research that can be done. Other things that we didn't cover is, if you have concept drift. So this is when, p of y given x actually changes slowly over time. Let's say, for instance, you have, behavior that's socially acceptable or not. As the norms change over time, that may change. Or, for instance, if you look at, email spam, that changes slowly over time, or maybe things that we consider, interesting or not interesting changes. So maybe initially all the fancy Facebook notifications were really exciting. By now we just file them away in some, nice to know folder. So there's a lot of different issues that you need to address. The one very worst case scenario for which there's really not much you can do is if you have a concept shift between training and test set. So that would happen is if, one thing is true on the training set and it's no longer true on the test set, and there's really nothing you can do about it. This is basically when somebody really gave you a malformed problem, and you should, be sufficiently courageous to tell whoever asked you to do that probably their data set is broken, because otherwise you just give them estimators and they consider themselves, having a good solution, whereas in reality they don't. Okay, so with that, that's the end of lecture number 7. Stay tuned for more.